So orbital control of climate. And these coupled aspects of the Earth's orbit are fondly called Milankovitch cycles. And it's very interesting now to recognize what the CO2 concentration was leading up to the emergence from the last ice age. And so if we're looking at the carbon dioxide mixing ratio in the atmosphere in parts per million, the end of the last ice age occurred right here 11,000 years ago, and that occurred just as CO2 hit about 260 parts per million. Now, as we'll see in just a moment, if we look at the situation today, the CO2 concentration is about 406 parts per million. And the other very important contributor to the trapping of infrared radiation is methane. Methane is now at about 1.7 parts per million. That's this point right here. But as we emerged out of the last ice age, the concentration was about 0.7 parts per million of methane. The other important contributor is N2O. That's also referred to as laughing gas. And when we look at the history of N2O, it was about 275 parts per billion as we emerged from the last ice age. And currently it's at about 325 parts per billion. This allows us to look then at the impact on the climate of this increasing concentration of these crucial molecules that absorb infrared radiation and radiate that infrared radiation back to the surface. So let's look then first at carbon dioxide. We know that its concentration has reached about 406 parts per million in the atmosphere, but that'll allow us to track the radiative forcing. That is the amount of energy coming back down resulting from the change in that CO2 concentration. And that turns out to be 2 watts per square meter. And if we look at the situation for methane, the forcing of the climate in that case is about 0.5 watts per square meter. And for N2O, that forcing is about 0.15 watts per square meter. So those three molecules dominate the trapping of infrared radiation. So if we look at CO2 and methane and N2O as a blanket over the Earth, infrared radiation moves through CO2, methane, and N2O, but also those molecules absorb and reflect this back down to the surface. So we've just calculated the forcing, which is the amount of energy per unit time, which is watts, per square meter, every square meter of the surface. And it's that downflow of energy, of infrared radiation, that warms the climate. So as we always do, we want to be very careful to link all of this back to the Gibbs free energy surface. And in this case, we're looking at carbonic acid aqueous plus water in the liquid form, creating the equilibrium that establishes the concentration of H3O plus, which provides the acidic character, plus the bicarb anion. And of course, the first thing we do is to calculate the change in Gibbs free energy for that reaction under standard conditions, and that's equal to plus 36.3 kilojoules. That is, the products lie at a higher free energy than the reactants. And on the face of it, you'd say, well, that means that the reaction is non-spontaneous, going from reactants to products. But then we remember the really important point that the change in Gibbs free energy is less than zero as we come down the curve from products to reactants. But so too is delta G less than zero when we move from reactants to products until we reach the equilibrium point at which delta G is equal to 0. And that means that the reaction indeed goes forward, forming H3O plus and the bicarb anion until it reaches that equilibrium point, and then the forward and reverse reactions exactly balance. Well, that allows us then to relate that reaction on a Gibbs free energy surface back to the climate, because now we can relate the carbon dioxide concentration parts per million to the radiative forcing. And once we can calculate the CO2 in the atmosphere and the response of the ocean carbonate system to increasing CO2, it means we can calculate the radiative forcing that results. And as I mentioned before, if you look just at the carbon dioxide concentration, that's about 406 parts per million now. But we have to also take into account increases in methane and increases in N2O. And when we do that, we are now sitting at just about 500 parts per million of CO2 equivalent, and that corresponds to almost 4 watts per square meter of forcing of the climate.